previous topics in this module have all been about understanding the properties of functions in general. We learned about their domains and ranges, how to transform them, how to compose them, and how to undo them with compositional inverses. Now we're going to look at a few specific functions which show up throughout the sciences. The first functions we're going to look at are exponential functions. But before we start construction of functions using exponents, let's review some of the basic properties that exponents have. First, if we take a real number a and a positive integer b, the expression a to the b stands for a times a times a and so on, b times. In this expression we call a the base, b the exponent, and we call the entire product a power of a. Instead of taking b to be a positive number, we can also take it to be 0, and then we define a to the 0 to be 1 in all cases. This is a useful definition since every time we increase the exponent of a power by 1, the new power should simply be the old power times a. So a to the 1 should be a to the 0 times a. For example, let's evaluate 3 to the 4. This power of 3 is 3 times 3 times 3 times 3, which is 9 times 9, or 81. The base here is 3. We have an exponent of 4, and this is the fourth power of 3, and it turned out to be 81. There are a bunch of rules for working with exponents. Once you become familiar with them, they make simplifying expressions and solving equations much easier. Our first rule for exponents is that a to the b times a to the c is a to the b plus c. What this says is that if we multiply two powers with the same base, we get a power whose exponent is the sum of the old exponents. Here's an example. 2 squared times 2 cubed is 2 times 2 for the 2 squared times 2 times 2 times 2 for the 2 cubed. Since we have 5 2's, we can write this as 2 to the 5. We could also have applied our rule to get to this point. Our rule simply adds the number of copies of 2 that appear in both products. We can also multiply this out to get 32 as our final answer. Let's look at our next rule. If we have a to the b, then we raise that all to the exponent c. That's the same as raising a to b times c. For example, if we want to evaluate 2 to the 4 all squared, we can compute this as 2 to the 2 times 4, or 2 to the 8, which is 256. If instead we evaluate 2 to the 4 before squaring, we get 16 squared, which is also 256. Why does this rule work? 2 to the 4 asks us to multiply 2 against itself 4 times, and then multiply that against itself. So we get two groups of 4 2's, or 8 2's multiplied against each other. Our next rule gives meaning to negative exponents. When we have a to the negative b, that's the same as 1 over a to the b, or the reciprocal of a to the b. Let's use this rule to evaluate 4 to the 3 times 2 to the minus 3. Using this rule, we see that this is 4 to the 3 times 2 to the minus 3, or simply 4 to the 3 over 2 to the 3, which is 64 over 8, or 8. We can also use our previous two rules for exponents to simplify this expression. We'd like to evaluate 4 to the 3 times 2 to the minus 3 by adding the exponents. But in order to add the exponents, we need to have the same base for both powers. So first, let's express 4 as 2 squared. Thus 4 to the 3 times 2 to the minus 3 equals 2 squared all to the 3 times 2 to the minus 3. This is 2 to the 3 times 2 times 2 to the minus 3, which is 2 to the 6 minus 3. That equals 2 to the 3, which is 8. Now that we understand positive and negative integer exponents, we'd like to look at fractional exponents. If we have a raised to the 1 over b, then we define this to be the bth root of a. This rule works with our previous rules about powers raised to exponents. For example, if you take a to the 1 over b and raise it all to the bth power, you should get a to the b over b, which is a to the 1, which should just be a. This tells us that a to the 1 over b must have been a bth root of a. For example, if we want to evaluate 8 to the 2 over 3, then we get 8 to the 1/3 all squared. So this is the cube root of 8 all squared. Since the cube root of 8 is 2, we get 2 squared, which is 4. Our last rule is that a product of two numbers, a and b, raised to the c, is a to the c times b to the c. So we can apply the exponent to both terms in a product. If we raise a fraction to the exponent c, then that's the same as raising the numerator to the c and the denominator to the power c. Let's evaluate the square root of this fraction. First, we can cancel 3 6's in the numerator with 3 of the 6's in the denominator. Another way to see this is that we can write the denominator using negative exponents. So our old expression is the same as the square root of 3 cubed times 6 cubed times 2 to the minus 1 times 6 to the minus 6. Adding exponents on the two terms with base 6, we get the square root of 3 to the 3 times 6 to the 3 minus 6 times 2 to the minus 1. Now let's expand 6 as 2 times 3. So we get the square root of 3 to the 3 times 2 times 3 all to the minus 3 times 2 to the minus 1, which is the square root of 3 cubed times 2 to the minus 3 times 3 to the minus 3 times 2 to the minus 1. Now adding exponents, we get the square root of 3 to the 3 minus 3 times 2 to the minus 3 minus 1. Now 3 to the 3 minus 3 is 3 to the 0, and so that's just 1. This leaves us with the square root of 2 to the minus 4, which is 2 to the minus 4 all to the half. And using our rule for multiplication of exponents, we get 2 to the minus 2, which is 1 over 2 squared, which is 1 over 4. You can try simplifying this expression in other ways. If you're using the rules correctly, you'll always get the same answer, 1/4. Problem 18 asks us to simplify the function f as given by this rational expression. In order to simplify f, we'll factor its denominator and then group similar factors. The denominator of f factors as x minus 2 times x plus 1, and this is all raised to the power of 2 over 3. Using our rule, we can distribute the exponent of 2/3 onto each factor in the denominator. Now we see that the terms in the denominator match those in the numerator. Let's look at x minus 2 to the 2 over 3. This is the same as x minus 2 to the minus 2 over 3 if it were written in the numerator. Therefore, we can add the exponents on the x minus 2 in the numerator and the x minus 2 in the denominator to get x minus 2 to the 1 minus 2/3. We can do the same for the powers of x plus 1. This leaves us with x minus 2 to the 1/3 times x plus 1 to the 3 over 3, which is just x plus 1. We can also rewrite x minus 2 to the 1/3 as the cubed root of x minus 2 if we like. In the preceding slides, we talked about the various rules for exponents. Now I'd like to introduce exponential functions. An exponential function is a function of the form f of x equals to a to the x. Here a is some fixed positive number. Unlike polynomials, where you have a variable raised to a fixed power, exponential functions have a fixed base and a variable in its exponent. Let's graph two exponential functions, one with base 2 and another with base 1/2. In order to draw f of x equals 2 to the x, we can plot some points. First, f of 0 is 2 to the 0, which is 1. So we know that f passes through the point 0, 1. We also have f of 1 equals 2 to the 1, which is 2. So we have the point 1, 2 on f. Next we have f of 2 is equal to 2 squared, which is 4. If we keep on going, f of 3 would be 8, f of 4 would be 16, and so on. We can also evaluate f at minus 1 to get 2 to the minus 1, which is 1/2. So filling in the curve, we see the shape of this exponential function. Exponential functions grow quickly as x increases, and decay quickly as x becomes very negative. They all pass through the point 0, 1. Let's plot g of x, the exponential function with base 1/2. Again, g to the 0 is 1/2 to the 0, which is 1. Also, g of 1 gives us 1/2. G at 2 equals 1/2 squared, which is 1/4. So here we see that g is getting closer to 0 as x gets larger. If we evaluate g at minus 1, we get 1/2 to the minus 1, which is 1 over 1/2, which equals 2. It's not a coincidence that f and g look like reflections of one another. You can see that g of x equals 1/2 to the x, which is 2 to the minus x, which is f of minus x. Thus we obtain g from f by a horizontal flip. That flip comes from the stretch factor of minus 1. In problem 19, we are told that f of x is a function of the form k times a to the x for some values of k and a. That is, f is a vertical stretch of an exponential function of base a. We are also told that f of 0 is 4 and f of 2 is 1. This is enough information to determine what a and k are. First, since f of 0 is equal to 4, we know that 4 is equal to k times a to the 0, which is just k. So k equals 4. Our function for f now looks like f of x equals 4 times a to the x. Since f of 2 is equal to 1, we have 1 equal to 4 times a squared, and rearranging, we get 1/4 equals a squared, and hence a equals 1/2 is a solution. Let's draw the graph of f of x equals 4 times 1/2 to the x. We have to take the graph which we had for 1/2 to the x from the previous example and stretch it up by a factor of 4. Notice that this new graph will pass through the 2 points 0, 4 and 2, 1 as we wanted. In fact, since any exponential function passes through the point 0, 1, when we scale it up vertically by a factor of k, the new graph will always pass through the point 0, k. What I'm saying is that a function of the form k times a to the x always has its y-intercept at height k. You may be wondering why we didn't consider the solution a equals minus 1/2. This is a solution to the quadratic equation we had before. However, exponential functions aren't defined everywhere when you have a negative base. For instance, if you evaluate an exponential function at 1/2, you get a square root of the base. If the base is negative, there is no square root of the negative number. So this is why we avoid negative bases. Now I'd like to introduce the most important exponential function. It's the exponential function with base e. The number e, which is around 2.7, is a special constant that shows up all over mathematics and the sciences. It appears in equations that involve growth and decay of physical quantities, and is important in everything from finance to biology to physics. The key feature that this exponential curve has is that it's the only exponential curve which has slope 1 as it passes through the y-axis. Let's draw the exponential curve. Like all exponential curves, it passes through the point 0, 1. And since it has base e, it passes through the point 1, e. When we fill in the curve, you can see that it has slope 1 when passing through the y-axis. If you have an exponential function with a larger base, like 4 to the x, it will be steeper. And if you have an exponential function with a smaller base, like 2 to the x, it will be shallower. Now that we've seen the graph for e to the x, let's graph some transformations of it. In problem 20, we are asked to graph 3 times e to the x plus 2. We can see that the graph for this function comes from the graph for e to the x, from translating it to the left by 2 units and then scaling up by a factor of 3. So the point 0, 1 moves left 2 units to minus 2, 1, and then scales vertically by a factor of 3 to give minus 2, 3. We can also see that this is what we get when we evaluate f at x equals minus 2. Let's plot these points. We see where 0, 1 is on our graph of e to the x on the left. Minus 2, 1 is a point on the intermediate graph y equals e to the x plus 2. And minus 2, 3 is a point on our final graph. We can also watch where the point 1, e on our original graph gets sent to under these transformations. The next function I'd like to graph is e to the minus x squared. Let's evaluate this function at 0, 1, and minus 1. F at 0 is e to the minus 0 squared, which is e to the 0, or just 1. F at 1 is e to the minus 1 squared, or e to the minus 1. This is 1 over e. Also, if you evaluate f at minus 1, you get the same answer out. 1 over e is a little larger than 1/3, so we can draw the points 1, 1 over e and minus 1, 1 over e on our graph. If we put a really large number x into f, then we see that we get e to a really large negative number, which is 1 over e to a really high power. This is a fraction which is really small, so our curve hugs the x-axis as we go out to the right. If we put a really negative value in for x, then since we square x, we still get e to a really large negative number, and thus the curve approaches the x-axis as we move to the left as well. Our final problem on exponentials is to simplify and graph e to the x plus 1 all cubed and divided by e to the x. Here we get to use our exponent rules. The numerator is really e to the 3 times x plus 1, or e to the 3x plus 3. The e to the x in the denominator can come up to the numerator as e to the minus x. Since we have a common base of e, we can add these exponents to get f of x equals e to the 2x plus 3. This graph comes from translating to the left by 3 units and then compressing horizontally by a factor of 2. So the point 0, 1, which is on e to the x, first moves to the left to minus 3, 1, and then its x-coordinate gets shrunk by a factor of 2 to get to minus 3 over 2, 1. So that's a new point on our graph. Since we know the shape of our curve for e to the x, it's easy enough to fill in what the rest looks like. You can also evaluate special points that you're interested in. For example, f of 0 is e to the 0 plus 3, which is e cubed, or around 27. On our next topic, logarithms, we will have more chances to work with exponential functions algebraically rather than just graphically.